Okay, so I'm going to try this recording the third time today, and we'll see if this actually works. Alright, so we've been practicing with a t-table. In the last video, we ended with where I was showing you how to use this t-table. Remember, this is a family of curves. Each one of these lines is representing a different sample size. Degrees of freedom that are down the side, this is just n-1. And then you find your confidence levels across the bottom. So if you do n-1, find the degrees of freedom, line it up with the confidence level, then we find the degrees, the t-star that goes with that. So we did a couple of them together. If we have a sample size of 10 and a confidence level of 90%, then we go to line 9, since we have a sample of size 10, and line it up with 90%, and that's how we got 1.833 as our t-star. And we did that for the next one. Now what was different was when we got to 50, that's a degrees of freedom of 49, but there is no line 49. Remember how we talked about this was a family of curves, and as our sample size gets larger, it's approaching the true normal curve. And as it gets larger, it's approaching it faster and faster and faster, and so you'll notice that these numbers aren't really that different. In fact, those are the same. As we jump by tens, and then we eventually jump by 20, and then jump up by 900. So since they're not really changing, there was no need for every line. So what you're going to do is, if the line, if 49 is not there, you're going to use the line 1 less than that. So the 1 less than 50 would be 40. So that's what line we're going to use. And we're going to state that. We're going to say, hey, we use this table and we use line 40, even though we know degrees of freedom is 49. And you line that up with a confidence level and get it that way. Same thing if it's 150, my degrees of freedom is 149, but there is no 149, so you're going to use line 100. Now, what if I want to do this on the calculator? Well, if you want to do this on the calculator, you're going to look for a function called inverse t. And on your calculator, if you go to second vars, inverse t is the fourth choice there. And what you're going to input here is, I'll just do the first one. Remember when we did z-scores, t's are the same thing. T's are measuring the same thing that z was. They are both critical values. They are both measuring the number of standard deviations you are away from the mean. So when I find t, that's the value on either side, the critical value, the number of standard deviations away on either side of the center we are, if I'm looking at the middle 90%. So I need the area in either tail. So if this is the middle 90%, then I've got 5% here and 5% here. So what you're going to input here, and if you have StatWizard running, it's asking you for these things. It's going to ask you for the area in the left tail. So that's 0.05. And then it's going to ask you for the degrees of freedom. So if my sample size is 10, my degrees of freedom is 9. Okay, so if you have the StatWizard, it's prompting you for both those things. If you don't, then just put them in separated by a comma. And then we should get the negative form, because we're looking at this one this side, right, of what we found from the chart. And it's exactly the same. So it's from negative 1.833 to positive 1.833, okay? Now, if your degrees of freedom was a specific line right on the chart, then what you get on the calculator should be in complete agreement with what we got on the table. Where it might be a little different is like here, where we used a different line. Well, if we use the calculator, I'm going to get a little bit different t-star. So if I go to second vars, inverse t, and I'm using a 95% confidence interval, so my area to the left will be 0.025. Degrees of freedom here is 49. And we see that the t-star we get here is 2.00, actually we'll round it up to 2.010. So slightly off from what we saw on the table. Because remember, this one was rounded. I do not care which one you use, but you must say how you got it. So if you're going to use this one, you need to say, I use line 40 on the t-table. If you use this one, you need to say, I use the calculator to find this. Okay? All right, let's try one more time for this last one. This is the last one. We do second vars for inverse t. And my calculator's died. Second vars, inverse t. Area in the tail is going to be 0.1, since we're looking at the middle 80%, so 10% on either side. Degrees of freedom is 149. And we get a t value that's pretty close. Okay, and you see as the larger you get, they're going to be real close together. Okay, so let's actually put all this together and run a complete confidence interval with means. Okay? And so to do that, let's talk about what needs to happen. Before I do that, I always have students say, well, how do I know to use Z and how do I know to use T? Because both are measuring the same thing, right? Both are measuring the number of standard deviations that you are away from the mean. Z is just measuring it in a normal curve, and T is measuring it in a T distribution. Well, here is a nice rule to remember, ZAPTAX. If it's proportions, you're going to use Z. If it's means, especially if you don't know the population standard deviation, you're using T. Now, if you know the population standard deviation, you could use Z, but it just as a general rule, if it's proportions, use Z. If it's means, use T. Okay? All right, so again, both of those are measuring number of standard deviations you are away from the mean. T is just a more robust distribution. It can handle a little more. It can handle a little bit of skewness where the normal curve cannot. It can handle smaller sample sizes than the normal curve can, and so it's something that allows us to do a little bit more than we can do with a normal curve. Okay, so let's actually run what it means. We are still constructing fabulous confidence intervals. You are still going to start with an introduction, which is just a restatement of the question that's asked. You are still going to check the conditions, and the first two conditions are exactly the same. Simple random sample and the 10% condition. Now, to check for normality, either n is large, and the central limit theorem lets us know we can use it, or the population distribution is normal-like, or, I'm going to add in one more, graph of data is symmetrical with no outliers. So to check for normality with means, either you have a large sample size and the central limit theorem lets you know that the sampling distribution will be normal-like, or the parent population is normal-like, or a graph of the data is symmetrical with no outliers. Okay, once you've checked your conditions, now we're ready for the formula. And on your formula sheet, you have this formula in words, just like you did with proportions. Statistic plus or minus critical value times standard error. So your statistic is either x bar or p hat. Well, we're dealing with means, so it's x bar. Plus or minus the critical value. Well, ZAPTAX tells us my critical value of proportions is Z, my critical value of means is T. And then times the standard error of the statistic. Now remember, standard error is just your standard deviation, but you're using a statistic in order to calculate it. And if you forget what they are, they're back here on the back of the formula sheet. See how for one proportions, there's a standard deviation, there's a standard error. Same thing, we just use p hat instead of p. Down here for means, there's a standard deviation, there's a standard error. Same thing, we just used S, the standard deviation from the sample, in place of the population standard deviation. Okay, so the standard error is just the standard deviation, but we're using the sample standard deviation here. Okay, and also one thing you'll want to state somewhere in your work is what your degrees of freedom are, because you've got to have that in order to find the T-star. And then your conclusion and context. I'm blank % confident that this interval captures the true whatever it is that we're trying to capture. So let's actually run one of these. All right, environmentalists, government officials, and vehicle manufacturers are all interested in studying auto exhaust emissions produced by motor vehicles. The major pollutants in auto exhaust from gasoline engines are hydrocarbons, carbon monoxide, and nitrogen oxides, or NOx. Researchers collected data on the NOx levels for a random sample of 40 light-duty engines of the same type. The mean NOx reading was 1.2675 and the standard deviation was 0.3332. Construct and interpret a 95% confidence interval for the mean amount of NOx emitted by light-duty engines of this type. So let's run through our steps. First step is the same exact step as proportions. I am going to construct, and I'm just going to restate the question. I'm going to construct and interpret a 95% confidence interval for the mean amount of NOx emitted by light-duty engines of this type. Okay. Now we're ready to check conditions. So first condition, it's got to be a simple random sample, and Up here it does say that they did a random sample of 40 light duty engines. So sample is a simple random sample. Sample is an SRS. Since it is a simple random sample, we've got to check the 10% condition. So the population has to be at least 10 times the sample size. So the population here would be all light duty engines. And what we're talking about with the light duty engines, that's like your smaller trucks, right? And I am pretty positive there's more than 400 of those, right? Okay, to assume independence, because that was why we checked that. Now, normality. How do I check that here? Well, my sample size is 40, and that's considered large, right? So I can say, since n is large, the central limit theorem says the sampling distribution will be normal-like. Okay, and now we're ready to actually run the confidence interval. Okay, formula. Our statistic, that's x bar, plus or minus critical value. Since we're dealing with x bar, our critical value is t, times the standard error. Okay, plug in. X bar, the mean is 1.2675, plus or minus t star. Now, if I have a sample of size 40, that means my degrees of freedom is 39, right? And I want to state that. But the problem comes when I go to look at my table, there is no line 39. So either I have to use line 30, or I need to use my calculator and find the exact t star. They're going to give me slightly different answers. I don't care which way you go. Okay, so I'm going to show both options on here, and when I check your work on a test or you're checked on an AP exam, they will have both answers in front of them. And so it does not matter which way you go, just make sure that you state what you're doing. Okay, so I'm going to show you both ways. No, you only have to do one. I'm going to do this with the chart first. So I'm stating on here, I'm using line 30 from T table. Okay, so I am telling them, hey, in order to do this next calculation, I am using line 30 from the T table. So for a 95% confidence interval, I'm going to line up 30 and 95% and find 2.042 times standard deviation is 0.3332 and sample size is 40. Okay, so let me crunch out the margin of error here. 2.042 times 0.3332 divided by the square root of 40, and I have a margin of error of 0.1078, we'll call it. And so if I subtract that, then I get 1.2675 minus 0.1078, about 1.16, I'll round. And then 1.2675 plus 0.1078, I get about, I guess that rounds up to that, okay? Or I could have used T star from calculator, degrees of freedom 39, okay? So here's how this is going to be different. So I would still show the same formula. I would still have the same mean, but I would find my T star by going to second bars, inverse T. This is a 95% confidence interval, so the area in one of the tails is 0.025. Degrees of freedom is 39, and so I get a T value of 2.023. So slightly different. So that means when I crunch this out, find the interval, it might be a little bit different. So 2675. 1.16 to 1.37. So pretty close, okay? But it is a little bit off because of that. And I will take either one. Just make sure you state which one you are using. Now, if it's a degrees of freedom that falls right on a line on here, whether you use the calculator or the table will not give you different answers, and you don't have to tell me. But if it's falling between the lines on the table, you're going to need to tell me which one you use, because it may affect your results slightly. Okay? All right, and then I finish this out with a conclusion. I am 95% confident that the interval from 1.16 to 1.37 captures the true mean NOx level for light-duty engines of this type. And honestly, because it's a measurement, I really should use grams per mile, whatever the units are. Okay. Now, you could check your work by using something called the t-interval. Remember when you did a interval with proportions, you could use the 1 proportion z interval, right? So you use 1 proportion z interval when it's proportions, or you use what's called a t-interval for means. Now, one thing to keep in mind is it's going to use this t-star, okay? So it might be slightly off what you would get by hand, but that would only be if it's not right on the line. So you go to stat, over to test, go down and find t-interval. You're going to have the choice between data and stats. If you're entering in all of the values, which we are, you're going to pick stats. If you had the data in a list, and I'll show you how to do that in a second, you would pick data. So we enter in the mean, 1.2675. Standard deviation is 0.3332. Sample size is 40. Confidence level is 0.95. And when you hit enter, you should get something very similar to this. And notice here, it also gives you the mean and standard deviation recalculated if you needed it. All right, so let me show you what happens if you have a list. So in class, we did this pulse activity. Now, just like I told my students in class, this was taken from my 6th period class today. All my conditions won't work here, none of them. I really shouldn't be running this, but I wanted to show you what to do with this data, so we're gonna go ahead and go with it anyways. I don't have a simple random sample. I have a very small sample. Technically, it's fairly symmetrical, so actually I could probably get around that since I'm using a t-distribution. But it's not a simple random sample, so technically conditions aren't going to work out here, okay? So I'm not going to run a full thing with this, but I just want to show you how you could enter this in your calculator. So what you would do is you would go stat edit, and what I'm going to do is clear out my list 1, and I'm going to type in all of these values into list 1, okay? So 48, 52, 56, 56, 60, 64, 64, 72, 72, 76, and 80, and 80. So there were 12. Oh, that should have been 48. Okay. That would be crazy to have a pulse rate of 8, right? Okay, so once you have in a list, if I want to run a t-interval and it looks like I'm running a 90% confidence interval, I would just go to stat, over to test, go down and grab t-interval. But this time I'm going to pick data. I'm going to say, hey, all my data is in list 1. My confidence level is 0.9. Hit calculate. And here's what's nice about this. Not only does it go ahead and give me my interval, there's my 90% interval, but it found the mean of all these values and the standard deviation, which I would need for the plugin. Okay? So when you're running these confidence intervals, if you are given the data, you can go ahead and just plug it in a list, and your calculator will do a lot of the work for you. Okay? All right, last thing I want to talk about is what to do when you are trying to calculate a sample size based on a margin of error. So before I get into this example, let's talk about what the margin of error is. Remember, the margin of error is everything after the plus or minus. So in a mean setting, everything after the plus or minus would be here. So it'd be t star times the standard deviation of the square root of n. Now here's a problem. If I'm solving for sample size, if I don't know sample size, is there any way I can find T star? I can't, and that's a problem. So anytime you're trying to find sample size with means, I will either need to be told a population standard deviation, because remember, we can't use Z unless we know the population standard deviation, right? Either I will need to be told the population standard deviation, or I will need to be told I can use the sample to estimate the population standard deviation. Because one of the main reasons I use T instead of Z is because I don't know the population standard deviation. I cannot use Z if I don't know it. So we're either going to be told an assumed population standard deviation we can use, or we're going to assume that the sample standard deviation is close enough. There's no way I can find T star in a situation like this. Okay, so in this situation, it says researchers like to estimate the mean cholesterol level of a particular variety of monkey that's often used in laboratory experiments. They would like their estimate to be within 1 milligram per deciliter of the true value mu at 95% confidence level. A previous study involving this variety of monkey suggests that the standard deviation of the cholesterol level is about 5 milligrams per deciliter. Obtaining monkeys is time-consuming and expensive, so the researchers want to know the minimum number of monkeys they will need to generate a satisfactory estimate. So we want it to be within 1 milligram per deciliter. That's our margin of error, right? I want it to be within that amount. So when I do my plug-in here, margin of error is 1. Z star is based on your confidence level, and if we have a confidence level of 90%, well, here, let's look at this. Remember on our T distribution, remember how all of these are our T values, right? And this is a family of curves, and as our sample size gets larger, we're approaching the true normal curve. And so guess what's on this very last line? This very last line are our actual Z stars. This is an easier way to find Z star. So you can do Z star with a Z table, or even easier, look right above 95%. Look what it is, 1.96. Right above 90%, 1.645. Because this is a family of curves, and as your sample size is getting larger, we're getting closer and closer to the true normal curve, that's what you have on this last line. All of these are T values, but this last line are actually Z values. So Z star for 95% is 1.96. The standard deviation we're using is 5, and then we're just solving for the sample size. So we just have a little algebra here to do. It's a little easier than with proportions. Square it. I got 96.04. So I need at least 97 monkeys. Okay, so I just divided both sides by 1.96. Multiply both sides by the square root of n. Then I said 5 divided by what I got here, and then squared it. And that's what I got. If you need help with that, let me know. All right, sorry for all the videos. I'm really hoping this one works since I've already recorded this lesson 5 times. Let me know if you have more questions, and I will be on Zoom, or I can create a Zoom if you need more help. Try these. Make sure that you're getting all the steps down, because the steps are the same way. You can expect to see one full confidence interval with proportions and one full confidence interval with means on the test.